part of the human civilization's progress throughout history. Structural engineering, a subdiscipline of civil engineering, is one of the major disciplines of this profession. Its history can be traced back when the first known architect, Imhotep, built the first step pyramid for Pharaoh Djoser back in 2700 BC. Well, pyramids were the most common important structures created by the ancient civilizations due to their innately stable structural type that may be essentially indefinitely scaled, as opposed to most other structural forms which cannot be linearly increased in size in proportion to increased loads. Progressively, as time passed, with the publishing of three major scientific works in the 17th century, Galileo Galilei, Robert Hooke, and Isaac Newton laid the groundwork for the contemporary structural engineering. Galileo published dialogues relating to two new disciplines in 1638, detailing the sciences of material strength and object motion, essentially defining gravity as a force, giving rise to constant acceleration. It was the first attempt to build a theory of beams, as well as the first scientific approach to structural engineering. This is also considered the start of structural analysis, which is the mathematical presentation of design and building structures. Throughout the late 19th and early 20th centuries, material science and structural analysis underwent development at a tremendous pace. Professor Hardy Cross's moment distribution approach, which allowed the true stresses of many complicated structures to be estimated fast and accurately, expanded structural engineering theory once more in 1930. Developments in the understanding of materials and structural behavior in the latter part of the 20th century have been significant, with detailed understanding being developed of topics such as fracture, mechanics, earthquake engineering, composite materials, temperature effects on materials, dynamics and vibration, control fatigue, creep, and others. The depth and breadth of knowledge now available in structural engineering, and the increasing range of different structures and the increasing complexity of those structures has led to increasing specialization of structural engineers.
Good afternoon, everyone. The previous reporter discussed about the history of structural engineering. Now, I am here to define what is structural engineering. Structural engineering is a specialty within civil engineering. It is one of the earliest types of civil engineering, going all the way back to when tree branches were lashed together with vines to form a shelter. It focuses on the framework of structures and how to construct them to endure the strains and forces of their surroundings while being safe, stable, and secure. What do structural engineers do? Structural engineers often work alongside with civil engineers and architects as a part of the construction team. If a structure was a human body, then the architect would be concerned with the body shape and appearance of the human person, and the structural engineer would be concerned with the skeletons, muscles, and tendons. Structural engineers develop drawings and specifications. They analyze blueprints, maps, reports, and topographical and geological data. They also estimate the cost and quantities of materials, equipments, and labor. They compute load and grade requirements, water flow rates, and material stress factors to determine design specification. They also inspect project sites to monitor progress and ensure the project is being constructed according to design specifications. They also conduct the study of traffic patterns or environmental conditions to identify potential problems and assess how will they affect the project. Structural engineers ensure that structures must be able to withstand the environment in which they are constructed. Like for example, Canada is so prone to winter. So, a house in Canada must have a roof that can endure the weight of heavy snow. And a stadium in California must be earthquake resistant because California is very prone to earthquake. Designers must then take into account the terrain, the water, the wind, and the traffic volume when designing bridges. All of these aspects are taken into account by structural engineers who offer technical advice on the project. They secure the safety of the environment. Now that you know what structural engineers do, let's talk about their salary. According to a website, salary.com, as of July 2014, a newly minted structural engineer with a bachelor's degree can earn between $41,000 to $62,000. A mid-level engineer with a master's degree and a 5 to 10 years of experience can earn between $74,000 to $102,000, while an engineer with a master's degree and more than 10 years of experience can earn between $87,000 and $113,000. Many experienced engineers with postgraduate degrees proceed to managerial roles to start their own enterprises, allowing them to earn even more money. While here in our country, according to the website payscale.com, a structural engineer salary in the Philippines for a newly graduated structural engineer with a bachelor's degree is approximately 27,000 pesos, while average structural engineer salary in Philippines is approximately will reach 400,000 pesos.
On the off chance that you incline toward a profession that ensures you guarantee the strength and integrity of bridges, dams, highways, and other structures, you certainly ought to consider turning into a structural engineer. So, how can one approach acquiring a degree in structural engineering? The initial step will be to earn a bachelor's degree in civil engineering. And if you wish to develop in your career, consider acquiring a graduate degree such as a master's degree in structural engineering. To obtain a degree in structural engineering, you must first pass the Fundamentals of Engineering exam. Following that, you must complete an internship as an engineering intern for at least 4 years under the supervision of a professional engineer to be eligible to take the Principles and Practice of Engineering exam. After finishing the P exam, you may be eligible to work as a structural engineer. Although state licensing requirements may differ, in most states, a 16-hour structural engineering exam counts as your P exam, with tests on vertical forces on the first day and lateral forces on the second day. Whereas in other states, an 8-hour test considers your P exam, with 5 profundity modules can pass towards the beginning of the day, and a specific test on one of the modules in the afternoon. And with that, you will be able to obtain your degree in structural engineering.
What do structural engineers do or work on? First is building structures. Structures like malls, schools, offices, and houses. Structural engineers that are working on building structures are the ones responsible for ensuring that the building can stand up safely. They make sure that the building will account for natural events, movements, and heavy loads. Furthermore, the structural design of a building can be very complex, and it requires a large team to complete. Second is mechanical structures. Structures like elevators, escalators, and different types of cranes. Structural engineers design these movable and moving structures that can account for stress and heavy load. They make sure that it can withstand different variations in the method in which load can be resisted. Another example for a mechanical structure that structural engineers work on are folding bridges.
Hello everyone, I am Clara Nikong and I'm going to continue the discussion with 2 more specializations of structural engineering. Structural engineers also specialize in earthquake engineering structures. These are, as its name implies, structures that are engineered to withstand earthquakes. Popular examples include the Temple of Kukulkan in Mexico, Taipei 101 in Taiwan, and the Burj Khalifa in Dubai. So what is earthquake engineering? It is an interdisciplinary branch of engineering that designs and analyzes structures such as buildings and bridges with earthquakes in mind. So it is basically concerned with protecting society, protecting the environment, either man-made or natural, from earthquakes by limiting the risks to acceptable levels. There are three objectives of earthquake engineering. First is to understand the interaction of structures with the shaking ground. Second is to foresee the potential consequences of earthquakes on urban areas and civil infrastructure. And third is to design, construct, and maintain structures to perform during an earthquake up to the expectations and in compliance with building codes. So if you were to sum up all these three objectives, the overall goal of earthquake engineering is to make structures resistant to seismic activity. Properly engineered structure does not necessarily have to be strong and rigid, like the Temple of Kukulkan as shown to you a while ago, or expensive like the Burj Khalifa. What's important is that it has to be properly designed to withstand the seismic effects while sustaining an acceptable level of damage. And of course, as a subdiscipline of civil engineering, structural engineers also specialize in civil engineering structures. While civil engineers may design roadways, tunnels, dams, and bridges, a structural engineer ensures that specific architectural components such as beams, foundations, columns, and floors are structurally sound. The objective of civil structural engineering is to create structures with adequate safety and serviceability under the influence of the relevant loads and actions during the lifetime of the structure. So this means that a structural engineer is responsible for designing and constructing physical structures to withstand earthquake pressures for a very long time. Structures include, but not limited to, bridges, dams, foundations, pipelines, power stations, railways, roads, tunnels, and water and wastewater infrastructures. These civil engineering structures are often subjected to very extreme forces, such as high temperature and high pressures, and they are also constructed in corrosive environments like underground or at sea. Thus, in the design of such structures, structural safety is of paramount importance. That is all. Thank you for listening.
Structures of aircraft, spacecraft, and missiles are designed, developed, and tested by aerospace structural engineers. Aerospace engineers can specialize in missiles and rockets, military fighter planes, satellites, helicopters, and commercial aircraft. They may also opt to specialize in areas such as instrumentation and communication, navigation and control, structural design, guiding, or manufacturing procedures. They also test prototypes to verify that they function reliably and create new technologies for use in space exploration, aviation, and the military. They are mostly employed in the fields of analysis and design, manufacturing, research and development, and federal government.